Hello, hello, anyone who's listening to this. So yeah, we've got these two different pure substances, right? And we've got what's called compounds. There we go. Try this again. So we've got compounds here. And then we've got elements. Why are you going so far sideways? Let's try this one more time. I'll get this right? It's just the first time, it's okay. Thank you, appreciate it. Yes, we've got compounds and elements. Now, difference between a compound and an element, just as a reminder, compounds are made of elements. That's what this arrow here is talking about, right? So if you can take a compound and react it with something, right, you can break it down into its elements, right? And then elements, this is what we're going to be talking about a little bit today, actually, is elements can be broken down into three families based on the periodic table, right? We're going to have, man, I am not doing great on this. All right. We're going to have metals, right? So that's things like gold and silver, iron, all of these elements on the periodic table, which are, hint, hint, black, right? So all the black text or black symbols are going to be metals, right? And we'll talk about that again in a little while, right? So then we're going to have, we have metals, we're also going to have non-metals, right? And so you would think, okay, we've got metals, non-metals, that should be it, right? Two groups, awesome. We covered metals, we covered the things that aren't metals. But then there's the really weird ones that they're neither. They are going to be metalloids, right? So kind of weird having something be metal, non-metal. Again, think you're done, doing good. We covered both of it. But then there's the stuff in between, right? Because the periodic tables, the elements are kind of weird. We'll just leave it at that, and then we'll cover that a little bit more. So everyone's got that filled out. You guys see how, if we've got, let's say I want to see what my smoothie is going to be, right? And if we can use this flow chart, right, we can think of it like those flow charts we did for the test tubes. We can say, if it's matter, we know smoothie is matter, right? Takes up space, right? Is the smoothie going to be a mixture or a pure substance? Mixture, right? Because it's got little chunks of mango, little chunks of little chunks of spinach, protein shake, whatever we want in there, right? So we know it's a mixture. Is it going to be a homogeneous or a heterogeneous mixture if I look at it? Right? If I blended this thing really, really well, or maybe I just went to like Jamba Juice or something, and they blend that thing for like 10 minutes, and I'm waiting in line wanting to get it, but it comes out and it's super smooth, really, small bits, and it all looks the same, right? It's just perfectly green or blue or whatever color you want, right? Is that going to be homogeneous or a heterogeneous mixture? Homogeneous, right? So this is going to be our smoothie right there, right? Now, what if I'm looking at, I'm thinking about going to a football game, crashing Davidson's little hideout in the booth and saying, all right, I'm stealing your salsa. I don't want the chips, I don't want the cheese, I just want the salsa, right? I don't know, maybe I brought my own chips, I don't know. But if we're looking at the salsa still matter, right? Yeah, it still takes up space. So then what are we going to say for if it's a pure mixture or a pure substance or a mixture? It's going to be a mixture, right? All right. So then if I'm looking at the salsa, it's got chunks of tomato, it's got chunks of jalapenos, onions, maybe some cilantro if it's a good salsa. Is it going to be homogeneous or heterogeneous if it's got all these different little chunks? Wait, what's that again, first hour? I can't hear you. Thank you. Man, this energy is just great. It's mostly centered here. just real wide awake. Yeah, but yeah, no, you guys are right. The salsa is going to be a heterogeneous mixture because when you look at it, you can pick out all the different bits and pieces, right? So yeah, and then we're going to talk now in just a second. If you guys would want to flip to, I think it's page 7. Let's see. Yes, page 7. We're going to talk about how to break up and distinguish this section, right? And in particular, we're going to look at how to differentiate between metals, nonmetals, and the metalloids. Sound good to you guys? All right, that's good. All right, so on page 7, let's figure out where presentation was, right here. Oh, also, reminder in case you weren't paying attention in the intercom announcements. Homecoming activity day is the powder puff game. Anyone doing powder puff? Woo! All righty. Cool. It's just flag football, right? Still tackle people. They can't catch you, just run fast. It's fine. All right, so and we already covered this. All right. But we'll do it again really quick. So before we get started on these physical properties of solids, I want you guys to find an empty space, probably in the top right of your page, and just draw 2 boxes for me and write down homogeneous and heterogeneous underneath them. All right, and they can be big boxes, little boxes, whatever you want to do. You could do it right above that QR code if you wanted to. All right, mind if I take a seat here? Might want to move the backpack if you would. Thank you. All right, so we've got these 2 boxes, right? And what I want you to do is draw for me. I don't mean draw like, okay, let me draw a smoothie, right? So that would be really cool if you could make like a smoothie look really good, right? I want you guys to draw for me what a homogeneous mixture and a heterogeneous mixture would look like, right? So just as an example, there's really no wrong answer for this. If I wanted to do like a heterogeneous mixture, I could just start putting little dots all over the place. If I wanted to, I could pull out a highlighter and start doing some more stuff on that. But go ahead and draw for me what that would look like for both the homogeneous and the heterogeneous mixtures. All right, and then compare notes with your partner and figure out what each of you are doing. See if you guys are doing it the same, and if you're doing it the same, figure out if you guys are doing it the same correctly first. And then if you guys are doing it differently, figure out why. There might be a correct answer for both of them that doesn't quite look the same as the others. So see, I'm seeing some good dots and squiggles and scribbles, and it's all good. Yeah, and I definitely recommend if you have like a pen or something, that really helps, because then again you can do, stuff in one color and then pull out another one, right? Pen or a highlighter, right? Do whatever you want to do to make some sort of heterogeneous mixture, and then the same for homogeneous, right? All right, so for me, what I would do is I would start with this, right? Heterogeneous mixture looks pretty good. I might add a little bit more here. I might add a star, some squares, circle, right? Just a lot of whatever, right? And then for homogeneous, I'm going to say I could either do something like this, where I just fill in the whole box with just a solid ink, right? Pretend that's solid, right? Or I could leave it entirely blank, couldn't I? Right? Because your paper's pretty homogeneous. It's the same white everywhere, right? Or if I was really, really meticulous, I could go through and make a grid system or a pattern of polka dots. It's going to take too long, but you get the idea, right? Just nice, evenly spaced dots, right? You could do either one of those three options. And I would say you guys would be correct, right? Now, if you want to test, because I don't know, maybe, hint, hint, we might be giving you guys a question, seeing if two pictures are homogeneous or heterogeneous. What you could do is you can break it down into fourths, right, on both sides. That was a little rough there, right? Break it down into fourths and say, okay, is square A the same as square C, right? A, B, C, D, right? Is square A the same as square C? What do you guys think? Yeah, I mean, they're both white. They both don't have any ink in them, or if yours does have ink, they both have the same amount of ink, right? What about for this one? If we've got square A, let's switch that to black so you guys can see that. We've got square A, B, C, and D. Are there any squares that are the same on this one? No, right? We got stars and circles and squares and all sorts of stuff that makes each of these boxes different, right? So that's just a quick recap on how to do those. Let's see. There we go. So again, we should all be on page 7, right? We're going to talk about the physical properties of solids. Hey, nice, that works now. So if we're looking at this, we're looking at how physical properties can be easily seen or measured without altering the identity of that substance, right? So if we were looking at the lab that we did yesterday, right? How did we figure out the physical properties of, say, sulfur? We just looked at it, right? Just saw it in the wayboat and said, oh, okay, it's yellow, it's powdery, it's whatever, right? We just looked at it, right? We didn't do anything to it. We didn't change what it was, right? So that's what this is talking about, is what other ways we can do to figure out what this is, right? So we've got 9 physical properties that we can observe and test for without changing the actual properties of the item itself, right? So if I'm looking at, let's see, if we're looking at Newman's shirt, right, it's gray, right? Me looking at it didn't turn it purple all of a sudden, didn't turn it stripes, right? Come on, it's stripe day, where are you at? Let's go. But yeah, so color, right? We can see that's pretty obvious, right? Color, just looking at something, it's not going to change, right? Unless maybe it's a chameleon, I don't know, right? And then solubility means, and this might be helpful if you guys wanted to define it. Solubility means if something dissolves in a liquid, right? Typically, that liquid's going to be water, right? So if we think of things that are soluble in water, we could look at something like a Gatorade packet, right? You guys are getting your pre-game hydration on and you're getting Gatorade, you put it in your water bottle, you shake it up a bit and you don't see the little Gatorade particles anymore, right? You don't see the grains of sugar and electrolytes and anything anymore, right? It's just perfectly yellow or blue, light blue. I don't know what flavor you guys like. I like the light blue one. But you don't see it anymore, right? If you guys are making pasta, right, and you're adding water to the pot and you're adding salt to that water, do you see the salt grains after a little while? No, right? So that's soluble too. What do you think would not be soluble in water? I'll give you a really easy one. You guys, right? You can spend all day in the pool and you're not gonna slowly dissolve into the water. We're not gonna have to like scoop you out with a pool net or anything, right? You guys all stay pretty much together in the pool, right? So that's solubility. Solubility, again, just means if you put it in a liquid, you don't see it as solids anymore. It fully disintegrates and becomes part of the liquid, right? Now, hardness, that just means if something's really hard, soft. If you've taken geology, I forget, do you guys have a geology course here? Is that a thing? No, no geology. Okay, I didn't have it either. I just remember this from like elementary school for some reason. So hardness, you can look at, okay, iron, right? If we look at iron, think of a nail, right? And iron can go into wood, right? So an iron nail is going to be more hard than the wood, right? So you can, again, look at how hard iron is without adjusting that property of it, right? Hitting a nail into wood doesn't change the fact that it's hard or sharp or brown or anything like that, right? So then our next set of three, we've got density, and we covered density, right? Do you guys remember the formula for density? Mass over volume. What's the cool tool that we gave you guys to remember how to figure out the equation for it? Tom circle, exactly, right? So mass, volume, density. All right, so we covered that one already. I'd say we're pretty good on that. Conductivity, what do you guys think that means? Right, if I say something's a good conductor, do you guys have any idea, any exposure to that yet? Right, yeah, I heard electricity. That's an awesome answer. Conductivity means that something will conduct or not conduct electricity. So if we think of things that conduct electricity, we can think of wires, right? Wires have metal in them. You can think of things like salt water, right? You always watch those movies of people getting lost at sea and there's a storm and the lightning striking it and they're all trying to swim away from the lightning because it's going to go through the water and get them, right? So what about things that don't conduct electricity? What goes on the outside of wires? Plastic, right? Yeah, plastic, rubber, right? There's a great story my dad has where he, when he was a kid, he had, I forget what they were called. Basically, he had waffle stompers, Doc Martens, right? Because he had really weak ankles. They were like laced up all the way to his knee because he had weak ankles and needed help. Well, waffle stompers have really, really thick soles, right? What are they made of? Rubber, right? Well, he, like many of you guys, had an older sibling. Older sibling said, hey, let's go down to the farm and we'll just hang out a little bit. So he, naively trusting his older sibling, goes down, thinks they're going to have a great time. And she says, hey, why don't you touch that wire over there? And you guys probably know this wire. You got some fence posts. If I can draw a fence post, that is. You got some fence posts, right? And then you've got maybe like some chicken wire or something, or cattle fencing, right? And then you've got this wire on the top here, and maybe it's got some little clips holding it in place. And you might hear a faint buzzing. You know which wire I'm talking about? Yeah, he didn't know. He didn't know what this wire was, right? So he grabs it, and again, he's in his waffle stompers, touches it, nothing happens. He doesn't feel a shock. He doesn't feel nothing, right? So his sister, of all people, says, oh, well, I guess it must not be turned on. She touches it, gets a shock of her life. Why? Because she wasn't wearing thick-soled waffle stompers, right? So wires and humans, us, we conduct electricity, right? Waffle stompers? No. Now, if you get struck by lightning, that's not going to help you, but you won't get shocked by the cattle fencing. So, all right, magnetism. This one, you guys can just highlight or underline magnet, right? And you guys looked at this last time, right, in the lab, where if you take a magnet and put it next to something, right, like iron filings or wood chips, you can see if it reacts. What happens when the iron comes into contact with the magnet? Yeah, it stands up, kind of goes all spiky, right? So if it does that, right, and we'll pretend this is our little well plate, and we've got a little magnet here. So that's what all magnets look like. It's going to make these cool little spiky formations, right, following the magnetic field. If something's not magnetic, what's it going to do? What did the sulfur do yesterday? Huh? It did nothing, right? Yeah, so it's just going to stay flat, right? So let's go on to our next three. Anyone got any questions about this? Preferably not questions about why my aunt made my dad touch a cattle fence. Also, please, guys, don't do that. That would be horrible, mean. Don't do that to people. All right, last set of three. We got melting point, boiling point, and odor. Right, so let's talk about melting point for a second. Melting point, you guys might know this better as something called the freezing point. Right? They're pretty much one and the same. Right? It just depends on what order or what direction you're going in. Right? So if you're starting with a solid and you're applying heat to it to make it become a liquid, right? We'll call that a melting point, which I abbreviate as MP, by the way. But if we're going from a liquid to a solid, we can call that a freezing point, which I also abbreviate as FP. Right? Now, what's something that we might be concerned about the freezing point for? Right? Winter's coming up. Right? What's everyone stocking up on? Hopefully stocking up on. This is Utah. Maybe you guys don't do this. Do you guys stock up on road salt for like your driveways and your sidewalks and everything? No? Okay, well, in Missouri, where we have loads and loads and loads of ice storms rather than snowstorms, because our winters are sad, we stock up on ice salt. And what's the big thing that it says on road salt? On road salt, you got your nice big package, right? And on the big fat label on the front, it's going to say lowers the freezing point of water by 25 degrees or anything like that, right? That's just telling us that, it's going to take colder temperatures to freeze it, right? You guys seriously don't get rock salt out here for your roads? Fair, but like, I'd rather not sprain an ankle on the sidewalk.
The city sprays the road, but they don't like spray it.
Well, no, like you don't spray it, but yeah, you guys don't do that? I learned something new every day. I didn't think I was going to learn that. Okay, then. I need to get a better example for freezing point then. Okay. But yes, that's freezing point or melting point. Both would be correct. Now, boiling point, has anyone here not lived in Utah the whole entirety of their life? I mean, yeah, we got Diego, of course, but all right, awesome. We like this. So what do you guys know about how the mountains affect how you cook pasta? Takes a little bit longer. And yeah, exactly. It's the altitude, right? If we look at, here's our mountains, right? And I'm going to put a little pot of water up here, right? And it's going to have steam coming off because it's trying to boil, right? And then we'll say I'm at sea level. I'm back home in Missouri, right? And I got my same pot of water boiling, right? Does it take longer to boil here or here? It takes longer in the mountains, right? That's because, weirdly, it's going to seem backwards to you guys, but in the mountains, water's boiling point is going to be lower, right? I forget what exactly it is, but it's something like 90 to 95 degrees Celsius, right? Whereas if you go down to sea level, where we use rock salt, and don't get sprained ankles on the sidewalks, it's going to be at 100 degrees Celsius or thereabouts, right? So what's that mean for pasta, right? If we're trying to cook pasta and we're a couple degrees short, it's going to take longer, right? Yeah. So that kind of makes sense, right? But boiling point, right? Just as from this example, boiling point is just when you can see bubbles forming and going up the pot that you have on your stove. I don't know why this is at a 45-degree angle, but we're going for it. So yeah, that's how, boiling works. Boiling just goes ahead and says this liquid, right, in here is going to start turning it into a gas, right? And it's going to start going up that was a horrible choice in marker. It's going to start going up into the atmosphere and being a gas, right? So if we clear this and make this better, so melting point is going between solid and liquid, right, in either direction. Boiling point is going to be going between liquid and gas, right? Now with both of these, if we use water as an example, if we've got ice down here, right, and then we've got liquid water, right? So what's in your guys' water bottles, right? And then we have gas, which I'm just going to draw like a little steam cloud, right? If we're going to Yellowstone, it's steam, right? Geysers and whatever. You know, are these all still H2O? Right, yeah, because we're not changing what the actual compound is, right? It's still going to be, you know, H2O here, H2O here, and H2O there, right? It's all still going to be the same, right? So that's what these two are really looking at, all right? So then our last one, this one's kind of weird, but odor, right? If we've got our test tube and we're safely smelling it by wafting it, right? Just because I want to make sure you guys are actually wafting correctly. Show me, you know, hold a fake beaker in your hand, right? Show me how you'd waft it. I like the Genovian wave going on in here too. Okay, yeah, I know I'm cultured, I got it, right? Yeah, so you're gonna waft it to your nose, right? So if we're slowly and safely wafting smells to our nose, are we changing what's going on in the test tube? Not really, right? Like the stuff in the test tube might be going through a reaction, but us smelling it doesn't affect it, right? It's just like looking at it, touching it, things like that. It's not gonna affect it, right? So odor is smelling safely, please. We don't want to burn any nostrils in the labs because it's not fun. You can't smell for like 2 weeks. It's a problem. All right. So that's our 9 physical characteristics. You guys need to go back. Anyone missing any of these? Thought I saw a couple blanks missing. I'm going to go back really quick. Our first 3, if you missed the first 3, right? We got color, solubility, and hardness, right? Next batch, density, conductivity, and magnetism, right? And then the ones we just covered, melting point, boiling point, and odor, right? Just want to make sure you guys have all those, all right? Because I'm pretty sure, correct me if I'm wrong, Mr. Davidson, but I think these will be some sort of matching or test question at the very least. Right. It's like if you get like 4 out of 9 of these, probably pretty set. All right, so let's talk about our first group of elements. Because remember on our, let's see if I can get a new, how do we do that? Aha. So remember our flow chart on page 5, right? Where we had elements and then we broke that down into 3 groups, right? Where we had the metals. What were the other 2 groups that we had? Non-metals, right? Heard that. And I also heard metalloids. Good job, guys. Metalloids. Let's see if I can spell. All right, awesome. Yeah, so we have these 3 types of elements, right? So we're going to go ahead and talk about those really quick. All right, so first we're going to talk about is metals, right? So metals, right? If you think of gold, silver, right? Those are all going to be metals, right? So we're going to have metals that are shiny or lustrous or have a luster, right? So if I remember right, this is the blank you guys need, right? So luster means that you could maybe see your reflection in it. You could see that it at least reflects light, even if it's not perfectly reflecting you, right? If you lose a ring in the middle of the night and you're going out with flashlights trying to find it, what are you guys looking for in the grass? Right, reflection of the light, right? So that's all luster is, right? And then good reflectors of light, it's similar to that, right? But it's just a little bit different, right? Reflector means that it's going to actually not displace it. It's going to, well, reflect it. There's not really another word for it. If I look at a mirror, right, which has silver, right, on the back of it, that's what mirrors are. It's glass with a lining of silver on the back. If I look at a mirror and I shine a light at it, right, it's going to go back, right? Luster is more that you can see the whole thing. It may not reflect it perfectly like this, right? But it's going to shine a little bit, right? So the next one, we talked about this a little bit before, right? When we're looking at conductivity as a physical characteristic. What did we say was a good conductor? Right, if I cut open a wire, which part's going to be a conductor? Is it going to be the inside or the outside of the wire? Inside, right? And the inside is made out of, oh, I heard metal, like a little faint whisper. Awesome, thank you. Yeah, so metals are really good conductors of heat and electricity, right? And some of us may have experienced how they were good conductors of heat yesterday, right? What did we do in the lab? We had Bunsen burners and we had test tubes. What were we holding the test tubes with? Test tube clamps, right? Yeah, that's what you guys are saying, right? Or thinking, because you guys aren't saying too much. That's okay. It's first hour. Tired. You guys had a late start. You guys could have slept in, but I don't know. I don't know what you guys do on your late starts, right? But if you were holding the test tube clamp, what was that made out of? You guys remember? Yeah, it's made out of metal, right? So if we've got metal test tube clamps or test tube holders, right? Those things may have gotten a little bit hot as we were going along, right? A little bit. I'm going to sit in the back here because I don't want to keep walking around. I feel like I'm walking too fast. Right? I'm getting steps in, but so with heat, right? We're holding this test tube over a Bunsen burner, really, really hot Bunsen burner. Why isn't it drawing? There we go. Right? And we've got this clamp test tube holder. We're holding on to that. And then I'm not going to try drawing a hand because that's going to be horrible. But if you're holding it here, right, and the test tube holder is getting hot here, will you guys eventually feel the heat? Right, yeah, it's like holding, a cast iron pan, right? You guys use cast iron at all?
Yeah.
Right, yeah, if you don't have a hot pad on your hand, right, even though the handle itself isn't hitting the flame, it's still going to get pretty hot, right? So that's what being a good conductor of heat is, right? You guys are pretty familiar with the electricity one because you guys all have phones, right? You can still charge your phones with a wire, right? And speaking of wires, right, ductile means that you can make a wire out of it. Oh, didn't mean to do that. Hang on. That was the one. So ductile is being able to draw something into a wire. And so what they'll do is they'll take a big block of it. If you've ever seen, I don't know if you guys have ever seen this actually. So you'll take a nice big block of your wire or your metal, right? Let's say it's copper wire, right? You take that and you heat it up a little bit and you start pulling it, right? And it'll start pulling out just this fine length of wire, right? And as they pull it more and more, it will get thinner, right? So if we're making wire to make like a cattle fence, we want it nice and thick, right? But if we wanted to, we could heat up that cattle fence and just make that really, really thin and turn it into, I don't know, chicken wire is thinner, right?
Yeah.
Yeah. I didn't grow up on a farm, but I know a little bit. So I'm trying to remember that sort of stuff because I think it's a good tactile and hopefully relatable experience. I don't know. You guys tell me, you guys know what chicken wire and cattle wire is, or cattle fencing? Why do we call it chicken wire and cattle fencing? It's the same thing. It's both fencing. Oh, okay. What do we call it then?
Barbed wire fence.
No, I mean like the big panels,
Chicken wire.
right? Well, if it's hexagons, it's chicken wire. If it's squares, it's cattle.
There's also channel fence.
Like panel? Oh, okay. Panel fencing. Sorry, I'm using the wrong terms here. Again, did not grow on a farm, trying to use examples that I'm not super familiar with. It's fun. All right, what do we got next here? Got one more. Oh, going too fast. So the last two ones that we've got for metals, we got malleable. So you guys can use foil, right? If you're trying to make, I don't know, I keep going back to camping because it works really well for this. But if you guys go camping or if you just want to do it at home, you guys make tin foil dinners, right? Yeah, you take your tin foil, or really it's aluminum foil, and you put your potatoes, carrots, I don't know, what else do you guys put in those? Meatballs, beef? Yeah, I use meatballs because I like to prepare that way, but it's tasty, right? So what is the foil made out of? It's aluminum. Well, we call it tin foil. It's not. Yeah, no, tin foil, we don't use tin a lot. It's weird, but we still call it tin foil. But it's aluminum, right? And if you guys haven't noticed, I'm trying to throw in a couple of elements in here for you guys as the symbol, so you guys can start working on memorizing, right? Yeah, I'm trying to sprinkle it in there, right? So we've got aluminum, and we can get aluminum as a really big block, right? I don't know why you would want a big block, maybe as a paperweight or something, right? But you can also get it as aluminum foil, right? And the way we get aluminum foil is, well, we do what it says. We hammer it over and over and over and over again until it gets really, really thin, right? We can do the same thing for gold, right? Have you guys ever seen those videos online of, $100 million desserts, and it's got like gold foil on a brownie?
Oh, yeah.
Right? It feels kind of, pretentious, but gold foil, right? You can have a gold ring, right? With a diamond on top or diamond not on top, whatever, right? You can have a gold ring, but you can also have, really thin pieces of foil that billionaires like to put on their brownies for no reason, right? But malleable, right? Because that's what you guys need to fill in. I think all the capitalized ones are fill-in ones. But malleable just means that you can make it really, really thin, right? And if we're just hammering it, right, does that change the composition of the metal at all?
Nope.
Right, it's still metal. It's still gold, silver, or whatever we started with, right? Yeah, so then our last one is tenacious, right? And tenacious means that you can't pull it apart, right? Or you can't pull it apart very easily, right? So if you have, let's say anyone got earrings or like a ring or a bracelet or something, right? If you try taking that in your hands and you try pulling it apart, you pull this way and hey, that worked out nice. And you try pulling the opposite way, you might bend it a bit. So I don't recommend doing it, right? You might make it into an oval shape, right? You might make it into a square, right? You might change the shape of it, but you're not going to fully break it, right? At least not if it's, iron or gold or anything like that. It's going to resist being pulled apart and broken, right? And that's what tenacious means, right? And so like if anyone ever tells you, wow, you're really tenacious, right? That means that even though you've got like a million different things, like you've got work, you got school, you got, let's see, who in here does sports? I know a lot of you guys probably do sports. Oh no, this is the class that only has like 3 or 4. But we got, sports, right? Maybe you got family, right? You're being pulled in a million different directions, right? But you're still keeping it together, right? Who's feeling like they're tenacious right now, right? We're a couple weeks into the semester. How are you guys feeling? You guys doing okay? Besides it being first hour and you guys being exhausted, right? But are you guys are doing okay though, right? All right. Every now and then we'll do a tenacious check, all right? Make sure you guys are keeping it together, right? Yeah, so that's metals, right? So what's our next one's going to be metalloids, right? So these are weird, right? Again, because you'd think that calling things metals and non-metals would cover it, but metalloids like to be special, right? Metalloids are pretty much going to be non-metals, right? So if they're not metals and they're non-metals, maybe we can't pull them into a wire. Maybe they're not ductile, right? Or maybe if we look at trying to make thin sheets of it, maybe it's not malleable, right? So for the most part, they have the same properties as non-metals, or they don't have the same properties as metals, right? This last thing, and then we'll call it quits. We'll come back to this tomorrow. They have semiconducting properties. Ah. All right, good job, guys. Thanks for making it a great first hour of me officially teaching. You guys are awesome. Try to get more sleep, please. I got to be able to hear you. Oh, that's